Hello students, welcome to class 12 physics. In this video we are going to solve numerical of textbook exercise of chapter 6 electromagnetic induction. Numerical number 5. A 1 meter long metallic rod is rotated with an angular frequency of 400 radian per second about an axis normal to the rod passing through its one end. The other end of the rod is in contact with a circular metallic ring. A constant and uniform magnetic field of 0.5 Tesla parallel to the axis exists everywhere. Calculate the EMF developed between the center and the ring. So, there is a 1 meter long metallic rod. It is rotated with an angular frequency of 400 radian per second about an axis which is normal to the rod. Through its one end, the other end of the rod is in contact with the metallic circular ring, and the constant and uniform magnetic field is parallel to the axis which exists everywhere. So here we need to find the induced EMF between the center and the ring, that is between this portion. So here EMF is equals to half B omega L square, that we had already seen in this equation in the previous numerical, how we have derived half B omega L square. So substituting the value, we get half, magnetic field is 0.5, angular speed that is 400, and here L that is nothing but the length of the rod, that is the distance between the center and the ring, which is 1. So when we calculate this, we get the value as 100 volt. Here if the axis of rotation is passing through the center of the rod, then EMF induced between the two ends of the rod will be 0, because in this case EMF between center of the rod and any one end of the rod will be epsilon dash, that is half B omega L by 2 whole square, which will be 1 by 8 B omega L square. Hence, EMF across the rod will be epsilon dash minus epsilon dash, that is equals to 0. So student, you may note down this numerical. Now numerical number 6. A circular coil of radius 8 cm and 20 turns is rotated about its vertical diameter and with an angular speed of 50 radian per second in a uniform horizontal magnetic field of magnitude 3 into 10 raised to minus 2 Tesla. Obtain the maximum and average EMF induced in the coil. Here we are having the radius of 8 cm, that is equals to 0.08 meter. We are having number of turns, that is 20. The magnetic field is 3 into 10 raised to minus 2 Tesla, and angular speed that is 50 radian per second. If the coil forms a closed loop of resistance 10 ohm, here we are having resistance as 10 ohm. Calculate the maximum value of current in the coil. Calculate the average power loss due to joule heating. Where does this power come from? So here first of all we need to find the maximum induced EMF. So maximum induced EMF, it is by the formula epsilon 0 equals to NAP omega. Here area is not given, but the radius of the circular coil is given. So taking the area as pi r square for the circular coil, so n pi r square b omega. Now substituting the values of n, r, b and omega and calculating that, we get 0.6029 volt. So induced EMF is equals to 0.6029 volt. Now instantaneous power, here we need to find the average power. So first the instantaneous power we will be finding, that is epsilon square upon r, where epsilon is equals to epsilon 0 sine omega t. So squaring it, we get epsilon 0 square sine square omega t upon r. So taking the average of that, this is the equation for instantaneous power. By taking the average, we take the average of this function sine square omega t, and the average of this function is equals to half. So average power will be equal to epsilon 0 square by r into 1 by 2. Now substituting the values of epsilon 0 and r, we get 0.6029 whole square by 10 into half. When we calculate this, we get the value as 0.01817 watt. So the value of the average power is 0.01817 watt. So students, you may note down this numerical. Now numerical number 7, of that we will be solving first the 7.1 part. A horizontal straight wire 10 meter long extending from east to west is falling with a speed of 5 meter per second at right angles to the horizontal component of the Earth's magnetic field, 0.3 into 10 raised to minus 4 Weber per meter square. So you can see over here the straight wire it is extending from east to west direction, and it is falling downwards with the velocity 5 meter per second, and it is perpendicular to that of the horizontal component of the Earth's magnetic field, that is towards the north is the horizontal component of the magnetic field. What is the instantaneous value of the EMF induced in the wire? Here we need to find the induced EMF. So epsilon equals to BVL, because it is nothing but BVL sine theta, and here the magnetic field and the velocity both are perpendicular to each other. So taking theta is equals to 90 degrees, so it is equals to BVL simply. So substituting the values of B, V and L, we get 1.5 into 10 raised to minus 3 volt. So student, you may copy down this numerical. Now 7.2. A horizontal straight wire 10 meter long extending from east to west is falling with a speed of 5 meter per second at right angles to the horizontal component of the Earth's magnetic field, 0.30 into 10 raised to minus 4 Weber per meter square. What is the direction of the EMF? So here also we are continuing with the same thing. The wire is placed in the west direction. It is falling freely in the downward direction, where it has the direction of the velocity. The direction towards the north is the horizontal component of the magnetic field, which is perpendicular to that of the velocity. So the EMF induced we have already solved in part 1. Now we will be finding the direction of this induced EMF. Here during the fall of wire, free electrons acquire vertically downward velocity, which is perpendicular to BH. The magnetic force on the electron, that is Fm equals to E into BH cross V, is exerted in the direction from east to west. So by using the Fleming's rule, we can get the direction of the magnetic force, that is from east to west direction. Hence, eastern end of the wire becomes positive by losing the electrons. That means all the electrons will be going towards the west side and east will become positive. So hence eastern end of the wire become positive by losing electrons, whereas western end of wire becomes negative by gaining electrons. The direction of EMF is away from the positive terminal. So we can say that the direction of the EMF is from west to east. So students, you may note down this numerical. Now third part of the seventh numerical. A horizontal straight wire 10 meter long extending from east to west is falling with a speed of 5 meter per second at right angles to the horizontal component of the Earth's magnetic field, 0.3 into 10 raised to minus 4 Weber per meter square. Which end of the wire is at higher electric potential? So this we have already seen that the west portion of the wire that becomes negative terminal and the east portion becomes the positive terminal. So the eastern end is said to be at the higher potential and the west end is said to be at the lower potential. So student, you may note down this.